Hello everyone, welcome back for another example, and this time it will be example 13. So first thing I would like to say is don't get the pizza from Pizza Pizza on campus. It's absolutely terrible. It is, usually I'm expecting Pizza Pizza to taste like cardboard, but honestly, this time they outdid themselves and it just tasted like charcoal. So yeah, there's that, and it's also really expensive for what it was. $6 for one slice. Like, not even you get two slices, it's just one slice. One small, tiny slice. Anyway, that was my short little rant. So, we have example 13, and I'm going to assume that you have it. No, I can't. Well, yeah, we're just going to go through and we're going to write it with nopes or stalls, not nopes, but stalls in particular. So the first one, we can just, since there's nothing before it, we can just write it straightforward, and that's going to be the load x10, 0, x13, okay? So that's the first one, the first instruction. Actually, I'll write it on the left-hand side because we'll have more space. So first it will be instruction fetch, then maybe zoom in a little bit more so I have space. Instruction fetch, instruction decode, execute, mem, and write back. And this was for load x10, comma 0, which is the offset, and then the base address 13. For future reference, this is RS1 and this is RS2. If you guys don't remember from specifically the assembly part, now we can go ahead and start with the next instruction. We're just loading stuff again, so no issues there. So we can just go ahead straight through, mem, right back, and again this was a load, and we're loading 2x11 with an offset of 8, and again that's from the stack or the base address x13. Okay, so the next one, which is an add instruction, and we are adding x10 and x11. Okay, so essentially what that means is that we have to wait for, because like let's read it out loud. Okay, so assume the perfect branch prediction is used, no stalls due to control hazards, that there are no delay slots, that the pipeline has full forwarding support, and that branches are resolved in the execute stage as opposed to the instruction decode stage. Okay, so that means our forwarding is basically resolved in the execution stage. In addition, stuff like control hazards don't cause any delay, but it doesn't say anything about structural hazards. In this case, we don't really have a structural hazard, so we're just going to have one delay, and that one delay is going to be right here. No, because we can go ahead. Yeah, it's going to be right here. The reason why it's right here is this x11 won't be ready till after the memory. Why? Because we have to add 8 and x13 inside the ALU, which actually happens inside the execute stage, and then it goes to the memory to read that value at that address and bring it forward to x11. Okay, and because of that, right, we actually have to wait for the memory to be done. And since we have to wait for the memory to be done, that's when we can forward it to our current execute stage. Okay, so that's exactly what's happening there. So this is the reason why we have to wait or input a stall there, okay? And then we're going to go ahead and we're going to write instruction fetch, instruction decode. Keep in mind this is a mem, this is an R-type instruction, so we're not using the memory, so that's why there's an exclamation mark there, and then we're writing that back to a register. Okay, so next we can, again, instruction fetch, and it's because we inserted a stall, we are going to have a stall for the remainder of the clock cycles here. Okay, so then we can go instruction decode, execute. Again, this is an add immediate instruction, so this was the add instruction right here. So add, let me go to it, it's x12, x10, x11, and then this one is the add I at x13, and x16. So again, we're not using the memory here, so we can just, say that with the exclamation mark. And we'll continue onwards to the branch not equal to. Branch, so is x12 equal to 0? Well, we don't know, but it says write it through twice, so we'll just write it. So it's going to be an instruction fetch, instruction decode, execute. So again, notice here, that's when x12 is available and we have full forwarding support. So we can assume that it goes there in a correct manner. So that's what's going on there. So execute, again, we're not using the memory, and we're gonna write back. Okay, so that was the branch not equal to 0. Okay, going forward, we have the second iteration. So we're gonna load our two values again, no issues here. So we can write it straight through. That looks a little sloppy. So let me rewrite that. So we have the instruction fetch, instruction decode, execute, mem, which we are using, and then write back. And then we have the second load. So this is load 1. So load 1, which is here. Okay, then we have the instruction fetch, instruction decode, execute, memory, which we are using, and write back. And that's load 2. This here is load 2. Okay, and here we're adding again. We're adding x10 and x11. So we're going to have the instruction fetch, same as before, instruction decode. We're going to insert a stall because we have to wait for the memory here. So then we can forward it to the execute stage so we can add it together. We are not using the memory, so we'll put an exclamation mark and we write back. Instruction fetch again. We have this stall here, so we had to wait. Instruction, this stall, by the way, this one right here, it's not like we're inserting a new one, it's just it happened because we needed it up here, so we're going to take this stall all the way through. It affects everything below it, but it doesn't affect anything above it. Okay, that's important to understand. Execute, memory, and write back. Instruction fetch. So this is add I, and then this is the branch, which again, we're not using the memory. So that's part A. Part B, what does it say? One moment. Part B says, mark pipeline stages that do not perform useful work. how often will the pipeline is full? Do we have a cycle in which all 5 pipeline stages are doing useful work? Begin with the cycle during which add I is in the if stage between with the cycles. So B, the answer it says, in particular clock cycle, a pipeline stage is not doing useful work if it is stalled or if the instruction going through that stage is not doing any useful work there. So for example, the memories in the add I, so like let me highlight it with so like these ones with the exclamation mark, that's unuseful work. Like it's just going there just for the sake of being there, and nothing's really happening there. So that's what it's talking about. So as the diagram above shows, there are not any cycles during which every pipeline stage is doing useful work. So there's no like vertically. So again, I'll use the highlight. There's no vertically or vertical line where all 5 stages are being used, right? I forgot a B here. So if we go ahead and draw them down vertically, not a single one is being used. Why? Like, for example, here, this one particularly, you might say, hey, the write back we're using, but I'm sorry to say we are not using that. Why? Because essentially all we did for the branch not equal to 0 is we went to the ALU, added 2 things together, and made sure, like we took the value of x12, and then we took x12's conjugate, and then added together, and if it was equal to 0, no, you don't even do that. You essentially OR together x12 and 0, x12 or 0, and if you OR it together and you have some one binary bit in one of the 32 bytes, or one of the 32 bits, then yeah, that's how the ALU would work. So you would essentially OR together the 0 or 32 zeros and whatever value is that, and if you have anything that's greater than 0, then yeah, then it loops. So that's what happened. And yeah, thanks for watching.